Hi,
Please stop talking.
my name is Russ Lagerwall. I work for Citrix on Zen and Zen Server, and I'm going to be talking about implementing secure boot. There is no audio.
In the room, so you need to actually keep quiet, and then you will be able to listen. The mic is only for the live streaming.
So I'm going to be talking about secure boot on Zen. So I'll briefly go into some background about it and why it's useful. So secure boot is basically a way of preventing malware from running at boot. So the worst thing that can happen is malware sort of affects the bootloader or operating system kernel image, and once it's got to that point, it can basically own the system. I mean, this could happen from like a rogue update or something. So there are a number of ways that it could happen, but one way of preventing it is to use secure boot. So the firmware basically has a way of working out whether the image is trusted or not, and preventing you from booting untrusted images. So this works well if you've got real hardware, but if you've got a VM in the cloud, for example, like running Zen, unfortunately it doesn't support secure boot at the moment. So what can we do about it? So just on some background, secure boot is actually part of the UEFI specification, just added in version 2.3.1. And this is basically a replacement for the BIOS, which is the firmware that sort of starts the operating system and provides some services to it. So the first thing to note is that, well, if we want to use secure boot, then we need to be using UEFI guests. Luckily, Zen does support UEFI guests already, so there's nothing for us to do. It makes use of OVMF, which is kind of like the build of the Tiana Core open source UEFI implementation tailored for virtual machines. Now, the way that UEFI starts the kernel or bootloader is kind of different from if you're used to BIOS. So with BIOS, it basically chooses a disk to boot and starts executing from the MBR at the beginning of the disk. With UEFI, the firmware knows how to understand GPT partition tables and FAT file systems. And so it's configured to boot a particular file of a particular file system. And this is sort of quite a lot like how an operating system would start some executable that it knows about. Now, when you turn on secure boot, there's an extra step. Basically, before executing that file, it verifies whether the file is trusted and can be executed. So how does this work? So hardware has NVRAM, which is kind of like non-volatile storage separate from the main disk. And these store UEFI variables, which are kind of like key value pairs. And some of them contain certificates. There are a number of them, and I won't go into the details of what they mean, but essentially the bootloader or kernel that you're executing needs to have been signed by one of these so-called trusted certificates. And therefore, if the kernel is replaced with something else, the firmware will refuse to start it because it hasn't been signed properly. The certificate databases themselves can be populated in a number of ways. One of them, which is probably the most common, is just that at factory install, the certificates are loaded into the NVRAM, and it just works because the laptop or whatever comes preloaded with an operating system, and so if you're running Windows, it'll come with the Microsoft certificates. If you want, you can update the certificates in the database. So these databases are called authenticated variables, and they require to update it. You make a sort of runtime call called set variable, but this update needs to be signed by specifically one of the certificates that's already in the database. And so malware can't sort of it can't trick itself into being trusted by inserting its own certificates in the database unless it can sign the update, in which case it could sign the bootloader anyway. The third way is typically there's like a platform-specific reset method. So on real hardware, you would say press F2 during boot and with physical access reset the certificates or clear them. For a VM, the way I implemented it on Zen was just in the hypervisor, or specifically DOM0, there'd be some button that you can press or command to run, and you can clear the database for a VM. So if we look at how this is implemented on real hardware, kind of the most important thing is that the code to update the set variable code in firmware which handles updating those certificate databases needs to be protected from being sort of interfered with, because if malware could interfere with this code and somehow circumvent the checks, then it would be possible to just insert your own certificates, or if it could write directly to the flash, then it's a problem. So there needs to be a way of protecting the code that's running, but it's kind of just, it runs on the same CPU that's executing the other code, which, it could be some sort of rogue device driver that's running as part of the operating system. So there needs to be a way of sort of defining an extra level of privilege or execution context. And on x86 processors, this already exists in the form of something called System Management Mode, or SMM for short. So this is kind of something that you can jump into and execute code from a special section of RAM called SMRAM, which is hidden from the rest of the system. So the sort of security sensitive part of the firmware is placed in that SMRAM, and the NVRAM is configured in a way that it can only be written from within SMM. So making a variable update then requires doing an SMI, and then it traps into this system management mode, and in theory it's secure, at least in theory. So KVM has implemented secure boot. The approach that they took it virtualizes what real hardware does. So QEMU emulates some flash memory, which is the NVRAM, and KVM emulates system management mode for guests. And it kind of implements or reuses parts of the Tiano Core firmware for the SMI handling and the way that it jumps into the sort of SMM part of the firmware. So there's a interesting talk by Paolo about implementing this on KVM, so I won't get into too many details because I'll probably get them wrong. So how should this be implemented on Zen? So there are kind of lots of vulnerabilities against SMM mode because it's kind of tricky the way that it's implemented, and so there are lots of ways of attacking it, all sorts of cache attacks. And the previous talk I mentioned about implementing it on KVM also details some of these attacks. In addition, Zen does not have any support for emulating SMM, so implementing it would require, could introduce more bugs, at least until they ironed out. Thirdly, using emulated flash kind of limits the flexibility of how variables are stored, because the code that writes to the flash is stored in it's part of the firmware which runs inside the guest. So this is kind of okay for regular hardware, but for VMs we want to be more flexible because you want to be able to import VMs, export VMs, migrate them from to different hosts. So it would be useful if you could have something that was a bit more flexible. So with virtualization, there are kind of already two distinct privilege levels or execution contexts, broadly speaking, the guest and the hypervisor. So using SMM is not really needed to create this boundary or separation. So what we propose is to run a daemon in DOM0, which for Zen would be DOM0, essentially part of the hypervisor, that implements the variable services outside of the guest itself, and then add a new module to OVMF, which implements the variable services by essentially proxying them to the daemon that's running in DOM0. So there are about 4 or 5 different variable services that it does this for. So this means that the guest does not have direct access to the code, so it doesn't need to make use of the special SMRAM. It doesn't have direct access to the storage, so there isn't anything specifically needed for the flash emulation. And it means that the variable storage can easily be abstracted into different backends. So you could use an SQLite database or a Zappy database or flat files, kind of whatever you need to use to get the situation done. So I'll just talk about how this works in a little bit more detail with an example. So let's suppose that the operating system wants to make a update to one of the certificate databases by adding a new certificate. So it would do this by calling the set variable call, which is a runtime service. It's sort of a bit like a system call to the firmware or a sort of indirect function call. And it would send the new data and sort of a signed authentication descriptor, which needs to be signed by one of the existing certificates in the database. So this goes into the proxy module in OVMF, which we wrote, which we called Zen variable, and it finds the set variable handler there. So that basically has some memory which it's set aside, and it serializes the function call parameters into this separate memory, and then makes an IO port write to a well-known port number with the address of that memory. This causes the daemon in DOM0 to wake up, which we called VARSTORD, and so it handles the IO port write from the guest. That basically unserializes the function call or it maps the memory from the guest, unserializes the contents of it, and works out which command to run. In this case, it's the set variable one, so it calls the set variable function, and this then proceeds with the regular behavior of set variable and all the various authentication checks. And if it's a successful call, which in this case, let's say it is, then it stores it in the Zappy database, which could be anywhere. For example, it could be on another host even. Once this has happened, the response is then written back into the memory mapped buffer. So it would be EFI success, just a simple status code for this. That returns from the IO port write, which then causes the guest to continue executing, and the Zen variable module basically unserializes the response and returns it back to the operating system. So there's kind of a clear separation between what happens in the hypervisor and what happens in the guest, which makes it quite easy to analyze from a security perspective. So just to go over that, so we wrote a daemon called FOSDEM which implements this, and at the moment there's a single backend which is the Zappy database, which is used on Zen server, but it's kind of written in a way that makes it easy to use other backends. And then there's a OVMF module called Zen variable, which implements this sort of proxy. And we've got it working on Zen at the moment, and so you can implement secure boot and test it with both Linux and Windows guests. I believe it could be used with KVM without too much difficulty due to the fact that, nothing in it is really Zen specific. So this could be a different approach to SMM. It's also not really a platform specific implementation. So SMM is kind of tied to the x86 platform as far as I understand. Whereas this, it uses an IO port right, but the same sort of approach could be used on any platform. So I've got a demo video which I didn't want to do it live since it seemed a bit risky, but so what I'm going to do here is start a VM. This is running on Zen server, and it's booting up in UEFI, and at the bottom right is the console log for FOSDEM, which is essentially logging the runtime service request that FOSDEM is handling on behalf of the guest. So you can see various get and set variable commands. I'm just going to check that the kernel reports that it has been booted securely. So Linux reports that secure boot is enabled. I think it's a bit small to see the back, but the video is online if you want to look at it afterwards. So what I'm going to try here is modifying the bootloader, what the firmware executes, and in a way that would not ordinarily cause it to, it should still boot afterwards, but because the signature is different, it's going to, the firmware should refuse to boot it. So I've just written FOSDEM 2019 to the very first string in the program. Then the VM is then restarted. And if all goes well, the firmware will stop and not boot the operating system. So this is a trivial example, but it kind of shows what, if malware tried to somehow patch the kernel. It's not very clear, but that's the UEFI way of showing that it didn't boot, which is not exactly the greatest user experience, but it's possible to then run the command manually or execute the bootloader manually, and you can see it says security violation, which means that secure boot is doing its job. So that just leaves when will it be available. Unfortunately, it's not yet been publicly released, so we intend to release it shortly, and it'll be announced on the Zen mailing list. So if you're interested, please look out for it there. And that's the end of what I've got to say. Are there any questions? Yeah. The question was, how does it relate to QEMU and how does it work with QEMU in stub domain? So at least as we've implemented it, it's a separate daemon that's completely separate from QEMU. So Zen has support for, they're called IRX servers, which and you can have them in separate programs essentially. So it's kind of not related at all. And if QEMU is in a stub domain, then this daemon could be anywhere else, including in a stub domain as well. Yes. Good.
Do you have working codes?
Yes. So the question was, do I have working code for the certificate and authentication stuff?
Close the door. The talk is not over.
The answer is yes. So the demo that I showed was kind of all working.
The talk is not over yet. Please close the door. You will have the time actually to enter the room.
Sorry, can you just repeat what you said?
The code is actually used when you actually do a KEK update
Yeah.
runtime.
Mm-hmm.
The code in your password that actually authenticates
Yeah.
updated variable.
Yeah, that's implemented. So I didn't have a demo of that because it's, I mean, not really much to demo there. But
How percentage of the time is spent on that compared to everything else? What is a lot?
you mean the implementing time?
Well, there's all these crazy rules, all these different setup boot modes.
I mean, it's kind of a few thousand lines. I don't think it's not super intense to write. Kind of also developed a fairly extensive test suite for it because it is quite complicated.
For all the mode changes, for
Yeah.
implied
Yeah.
automatic variables, you have code for all that.
Yeah. So I mean, that is kind of the disadvantage of this approach is that it has to duplicate some of the code that's already been implemented in OVMF. But well, I mean, it's a few thousand lines of C code, so it's not terrible.
You mentioned in the slide with the architecture that FOSDEM has too much memory.
Yeah.
Wouldn't it be better for security if everything was sent like serially marshaled and unmarshaled so that you don't have like time of check, time of use, vulnerability, stuff like that? Are you still in time to update the protocol to make it more secure, or is it more or less like
Well, I mean, it maps the memory, but then copies it out of the memory that it's mapped before it uses it. So I don't know what you mean about how else would it get it if it didn't map the guest memory.
Yeah, I don't know. So the problem with this is that with SMM you have known problems with SMM. You can use them to bypass secure boot.
Yeah.
But with this, if you actually find a vulnerability in VASTOD, you escape to DOM0. So the difference is that with SMM, the bugs stay in the guest.
Yeah.
Here, the bugs go to DOM0. I agree that it's probably not hard to audit for things that are as trivial as time of check or time of use.
Yeah.
But still, it seems to me that the good design would at least eliminate the possibility of them happening.
So the question was basically how is the question is how is the security of FastLD handled because it's running in DOM0, so it's kind of an extra attack surface. So at least for how we've implemented it on Zen server specifically, it runs kind of sort of with no privileges in a sort of container environment, and so even if you could escape into DOM0, it should be contained, yeah, and you can't really escape out of that extra jail kind of thing. There's a question at the back.
Can you run the DOM0 bits in the stub domain or service domain?
Yes, that would be, so the question was, can you run the DOM0 bit in a stub domain? So that would be, the answer is yes, that would be another approach to removing any potential security risk of running it. So, yeah, either within a jail or some kind of stub domain. Question?
Is there one FOSDEM for all VMs, or is there one for every VM?
It's a separate instance. Is there one FastLD for every domain? The answer is yes. It's a separate instance, kind of like the way you get a separate QEMU for each domain. So time's up. You can find me afterwards if you want to ask any other questions. Thank you.